Good morning, everyone. Thank you for having me here. So I'll probably start with yeah, some of my colleagues were telling me yesterday Corteva had a booth here, and a lot of people are wondering Corteva is an agriculture company, and many people have not even heard about Corteva. What is Corteva doing here in a sensor conference, in a technology conference, right? So I'm going to answer some of those questions using the slides here. And Corteva is a pure agriculture company. Two main products are seeds and crop protection chemicals, your pesticides, herbicides, all these things. And so a lot of R&D, research and development goes for this to develop these products, right? To develop seeds, plant breeding, and also to develop all your crop protection chemicals. So Corteva uses technology primarily in two different spaces. One is we directly work with farmers to collect data in farmers' fields. That's one thing. And then to develop these products, you need to do a lot of testing in field. So that's and in the field we collect a lot of data. In this particular case, I'm in field phenotyping. That's called field phenotyping, and I'm going to talk about how we use technology in field phenotyping. So, especially this presentation is relevant to seed product development, not the chemical part. So when you develop a hybrid variety, right? So it's like this funnel. You take with you start with let's say thousands and thousands of hybrid seed native varieties, inbred varieties. Then you cross them, you develop hybrids, and as you go through the cycles, uh, one typical cycle lasts for almost 7 years. And as you go through multiple seasons in your cycle, you collect a lot of data in the field, and using that data, you either discard some hybrid varieties or select some hybrid varieties until commercialization, when you end up with only few varieties that you can actually commercialize. So earlier, if you consider the paradigm, like let's say 15 years ago, it used to be a lot of manual data collection in the field. Breeders who are experts in that particular crop variety or in that particular trait, they would go visit the field, look at the plants, and let's say they're scoring for a disease severity, right? They would actually use their expertise to score plants after visually looking at them on a scale of 1 to 9, let's say. But problem with that is a lot of subjectivity. One scientist would say this is a 3, and one scientist would say this is a 5. And then the other challenge is throughput. It's extremely slow, low throughput. And then you also have temporal constraints, like there's a lot of labor cost involved. And because it's so slow, you cannot actually collect temporal data. And then driving to remote fields and collecting data, I mean, it's a 1,000-acre field, right? Walking inside the field, it all has its own safety issues. Now, years ago, not just Corteva, across the industry, there has been a lot of use of technology in collecting this data. So few use cases are there, using drones, using your mobile cameras, using a lot of on-farm equipment sensors to basically collect data. If you collect data this way, it increases your throughput, it becomes more objective, it's more sustainable for high throughput data collection. So the journey of Corteva for question phenotyping started actually with drones. We purchased our first drone in North America in 2012. We did a lot of experimentation with that, started collecting data. Once we got confidence about data collection with drones, we expanded our fleet in 2014, and then we started working on the algorithms to process that data as well. And then from 2016, we started basically purchasing drones for other countries wherever Corteva research sites are there. It started with North America, then Europe, then Brazil, India. We have a lot of drones in India as well now. And then by 2018, we have built a automated pipeline that can actually take the data that's collected using drones and generate the insights that breeders can use in their selection um, process. So typically, the bottom you see, right? That's how a drone UAS pipeline looks like. You collect multiple snapshots of the, if you imagine your research field as a rectangular block, you collect multiple snapshots of the, you send your drone, collect multiple snapshots of the field, and then you stitch them together to generate a single automosaic of the entire field. Then you have a shape file that's actually generated using the planter data, at least the planter data. And if you overlay your shape file on the automosaic image, imagine a quick basically, and you get your plot level images, and each plot represents a single experimental unit which belongs to a single hybrid variety in the field. And then you process these images basically generate a trait value, whether it be disease score, or how green the plants are, or a nutrient deficiency, things like that. And then when we initially started, right, it was all very basic conventional image processing kind of methods. We would use thresholding to segment the plants in a image and then generate basic features like plant greenness, plant cover, some features representing health and maturity of the plant, things like that. Then we, in addition to basic RGB, we started using photogrammetry techniques to generate digital elevation maps to basically capture plant height related features as well. And then we moved forward, and with machine learning and deep learning, we started using deep learning a lot on these images, and all these standard image processing computer vision techniques like detection, image classification, semantic segmentation, these sort of things to generate additional insights for readers. I'm going to talk about few examples here. This is one we published long back. So basically there is a nutrient deficiency that happens in soy plants. So our breeders were earlier using this manual 1 to 9 score to look at the plants in a plot, and basically based on what they see, if the plants have yellowness or the plants have shrunk, they would score them on a scale of 1 to 9. 1 is very sick and 9 is a healthy plant. So we started with a simple thresholding based method to segment out the plants and then extract some features based on greenness, color, cover, and all those things. And we trained simple linear regression models on those features to actually replicate the 1 to 9 scoring. And we ended up actually, instead of 1 to 9 scoring, we ended up developing a method that actually generates continuous scores. That gives even more granular data for the breeders to make their selections. And one of the, the advantages with this is because it's so objective and it's so consistent, and sometimes you're actually seeing something that human eye cannot see, or maybe human eye can see but cannot identify, and that can actually lead to novel insights. And then another example. So if you see on the left, right, someone is actually using a scale to measure the plant height of a corn plant on a cornfield. So that's, if you imagine doing that for 100 acres field, right? So how time consuming it is. So now with drones, right, you can actually take multiple overlapping images of the field, use photogrammetry, generate digital elevation map, and use that DEMs to generate plant height, which is actually quite important for breeders to make their selections. So I talked about drones, RGB-based sensors, right? In addition to drones, we have in the past 3 to 4 years, we started experimenting a lot with LiDAR sensors as well. We used Velodyne LiDAR sensors and generate a lot of data. And the idea is, I talked about DEM, right? DEM, though it sounds that it can do the job, but it's not that accurate. So we have been trying to replace that with LiDAR. And with LiDAR, it's not just height. You can actually generate features like canopy volume, additional features that earlier breeders probably would not have thought that they could look at those features to make their decisions. And then we have been using satellites, all these high resolution commercial satellites to actually do phenotyping. We did not even think that it would be possible 5 years ago. And then hyperspectral imaging, multispectral imaging, and then the next step is basically collecting video data using sensors on your mobile phones, like iPhone comes with LiDAR as well as high resolution cameras. And then also mounting some of these sensors on the farm equipment itself so that you don't have to actually go again in the field, because when you harvest, you're anyway taking your harvester into the field. What if you just mount your sensors there and collect data while harvesting itself? And then the next step is autonomy. So drones, right, the pilot has to fly. But then there are new concepts like drone in a box, basically automated drone where a pilot sits in a station somewhere and it's there in the field, but they can operate. And all this automated, I don't know if many of you heard about this robot called Solix robot. Solix robot is a new big robot that's completely automated. It can navigate through the field by itself. And farmers are actually using in North America and Brazil, I think, for automated spraying and things like that. And we are actually trying to leverage that robot to add sensors and then collect data. And then few more examples here using the iPhone. So this is not yet completely automated because in this case, right, we're trying to collect data about corn kernel level, how much scatter is there, how many kernels are there, what kind of disease is there, these sort of things using iPhone imaging. But in this case, the corn ears are still to be harvested. Actually, you have to manually harvest them, keep them in the pile, and lay them on the floor, and then take the imaging. But the ideal situation would be image the ears while harvesting with the harvester itself. And then another example in canola, where you have to look at the cross section of the stem and then score them further. So this is also semi-automated. You have to manually cut the stem, then image it, then you use object detection models and then classification models to score each individual stem on a scale of 1 to 9, or in this case, I think 1 to 9. And one thing we observed is past 5 years, earlier we were not really confident about this data, but with the methods and with deep learning advances in the last 5 years, we see that there's a lot of, I mean, we are not only agreeing very well with what manual data says, but we are also able to generate additional insights in addition to the manual data. And those are few examples. I think that's few examples of how Corteva is using technology in phenotyping space. And it's really an instrumental part to develop superior hybrid varieties. And then the more and more advances that are happening in this space, it facilitates better phenotyping. Better phenotyping means better products for the farmers, more yield, better for agriculture in general. So it's an exciting area with a lot of opportunities and a lot of challenges. Thank you.
Got a question in the back. Time for a couple of questions. So one there, one here.
Hi, this is interesting. So when you're using cameras to capture images in terms for phenotyping, what kind of cameras do you, are these multispectral cameras or are these RGB cameras?
I think 80% of our data is RGB, but there is a lot of multispectral data as well,
Right.
and LiDAR as well.
So which one do you think is going to give us the most important or interesting data points?
See, the reason that I say that 80% of data is RGB is easy to capture and easy to analyze, right? But if you ask me, multispectral having basically additional bands gives additional information, and that's more valuable in my opinion.
Yeah. Thank you.
So, see, what I understood that, you are trying to do mostly the physical parameters. So do you have any plan to expand this towards looking for the, say, soil parameters, micronutrients, those sort of characteristics?
Yes, they're already happening, but not within the scope of our group, within Corteva, but outside our group, it's already happening.
Yeah, so you are talking about drones integrated with the micronutrients of the plants, the different soil parameters.
I'm not sure if it's happening with drones, but I think it's mostly physical sensors that actually people carry in the field.
But not remotely sensed, right?
Remotely, I am aware of moisture and for irrigation that they use.
But no chemical.
For nitrogen, I know that they're using, but other nutrients I'm not really aware